All right, this week we're going to be talking about energy. Take a look at this picture here. We see a whole bunch of different types of energy, from light bulbs to fire to electricity, energy drinks, things like that. And we're going to talk about what energy is today. Don't forget, red slides mean you need to write something down in your notes. Don't forget to look for the owl. You're going to have to describe where he is. And remember, you also have to do a summary at the end. So you may have heard the saying before that there's no such thing as a free lunch, which means you can't get something for nothing. And in science, this is especially true. We can think of the universe, which is everything that exists, as sort of being contained within a jar. Now, this isn't actually true, but we can think of it this way, like it's a tightly sealed jar and nothing gets in and nothing gets out. So what I mean by nothing, well, I mean stuff, like these stars that you see here, and things like atoms, water, trees, plants, planets, everything. Nothing gets in and nothing gets out. So all of the atoms that are in the universe have always been there and always will be there. Same thing goes with energy. No energy comes into this jar, no energy goes out of the jar. The total amount of energy we have stays the same all the time, which means that if you gain some energy, you must have gotten that energy from somewhere in the universe. And if you lose energy, that energy has to have just gone somewhere else in the universe. Things just go from one place to another. This is what we mean by the law of conservation of energy. We'll come back to something like this later when we talk about the law of conservation of matter, but they're both basically the same thing. It means that nothing is created or destroyed. It's only changed from one form to another. Okay, so we understand that there's a certain amount of energy in the universe and it doesn't really go anywhere. It just changes from one type of energy to another, and we'll talk about that a little bit more. But before that, what exactly is energy? I think when we talk about matter, when we talk about stuff, we can point to those things and it's pretty easy. Energy is a little bit more difficult to figure out. You might think of it as like electricity, or you might think of it as the energy you get from a candy bar or something like that. But what exactly is that? Well, in science, we define energy as, first of all, the ability to do work. So it's the ability to do things. And another way of thinking of that would be to say it's something that causes something to move or to change in some way. So anytime something moves or anytime something changes in some way in the universe, you need energy to do that. So the law of conservation is that energy is neither created or destroyed. But let's talk about that second part, that it's only changed from one form to another. Okay, so I want you to try something out. This is a really good example of the idea of changing energy from one type of energy into another type of energy. So I want you to take your hands and kind of go like this. You've probably done this before, and you know that as you rub your hands together, you should start to kind of feel your hands kind of warming up. This is an example of energy changing from one form to another. You can think of your hands moving as being one type of energy, the energy of movement, and that energy is being changed into heat energy that we can feel in our hands because of this thing that we call friction, this sort of rubbing together of two things. So this idea of energy being changed from one form to another, and especially the idea of movement energy being changed into heat energy, is described by what we call the laws of thermodynamics. And if you look at the name of that, you know that thermo, the thermo part of that word, means temperature or heat, right? You know that from thermometer, you know that from a thermos or from thermal underwear, things like that. All of that has to do with heat. The word dynamics, that means movement. So this word literally means heat movement. So the law of thermodynamics is the movement of heat or the movement of energy. The first law of thermodynamics, and this is the first of three, says that energy is transferred but not destroyed. This is really just a restatement of the law of conservation of energy. We basically already talked about this. So the first law of thermodynamics is really just the law of conservation of energy kind of restated. So you've probably seen these before. This is called a Newton's cradle, and this animation's not bad, but there's something wrong with it, and that is that the real Newton's cradle doesn't keep going like this forever. And so why does that happen? Things tend to kind of slow down and come to a stop eventually. Well, the reason for that is because, again, friction, just like with your hands rubbing together, every time that one of these balls hits into another ball, there's a little bit of friction between them, and so they lose some of that energy. And just like with your hands, some of that movement energy is being changed into heat energy. This is basically what's described in the second law of thermodynamics. Energy is lost in quality due to friction, force, heat. Basically, it means nothing really lasts forever. Nothing keeps going forever. And notice that this is saying that it's lost in quality, meaning it becomes kind of less useful. You can see the two pictures here. You can imagine trying to skateboard, and eventually your skateboard is going to slow down. Same thing with the picture on the right. This is a car engine, and the way a car engine works is basically by making little explosions. Well, what that means is that some of that energy that you want to make the car go, that's coming from the gasoline, is actually just going towards heat and not really very useful, because we want that energy to make the car move. We're not really trying to use it to heat up the car. So this is the idea that whenever you're doing something, basically things are going to slow down and come to a stop because some of that energy is being lost due to friction. This is kind of unfortunate because it would be really nice if we had something like this, which is called a perpetual motion machine, where this thing kind of seems like it should be able to just keep going forever and ever, but it doesn't, because eventually those balls will kind of slow down and they won't be able to get back to their starting point because they've lost some of their energy due to friction. Last but not least, the third law of thermodynamics says that as atoms become colder, they slow down. When they reach absolute zero, the atoms actually stop moving. As far as we know, this absolute zero thing is not something that really occurs anywhere in the universe. Atoms are always moving, even in an ice cube or something like that, or a table. Atoms are always moving. But we haven't really talked about atoms quite yet, so I want to show you a quick little video here that gives you an idea of what atoms look like.
Have you ever seen an atom? Seeing as everything's made of them, you have, but have you ever seen one on its own? Over time, microscopes have become more and more powerful, allowing us to see deeper into the world of the ultra-small. Traditional light microscopes can be used to see things like these onion cells and the structures within them as they divide, pulling apart their chromosomes. But scientists have come up with a whole host of clever methods to observe far smaller things. Using beams of electrons instead of light, we can generate detailed images of chromosomes themselves. Recently, groups of scientists around the world are becoming able to see materials at the most fundamental scale, the atomic. One group from the University of California in Los Angeles have been getting up close and personal with nanoparticles of platinum, just a few nanometers across. Each of the tiny dots you can see here are actually individual platinum atoms.
So now you have a basic idea of what atoms look like. We really don't have any clearer picture than that. We've never seen atoms really close up, but we do have a lot of ideas of basically what they look like. But for right now, you can just think of them as like little spheres, and everything is made up of these things. And even in solid objects, these things are in constant motion. This is what it would look like for a solid object, that they're kind of vibrating in place. For liquids and gases, they move around a bit more, but basically they're always constantly moving. And the idea of heat, the concept of what we mean by heat, is really just a measurement of how fast those atoms are moving. The faster they move, the hotter the object is, and the slower they move, the colder the object is. Okay, let's talk about potential and kinetic energy. Take a look at this picture here. This picture shows a roller coaster, and we're going to use a roller coaster to demonstrate this idea of potential and kinetic energy quite a bit. And you can see just from this picture that potential energy is high and kinetic energy is low when the cart is at the top of the hill, and it's the opposite when it's at the bottom of the hill. And for just a second here, I want you to think about when that car is going the fastest. When something that you push down a hill is at its fastest. So it starts off at the top of the hill here, and it's not really going very fast at all. In fact, it's not really moving at all at this point. But as you go down the hill, it goes faster and faster and faster and faster and faster and faster and faster. It's speeding up the whole time. So it's right around this point, right near the bottom of the hill, where the car is actually going the fastest. And notice that that is the point where the kinetic energy is the highest. So we can kind of, in a very simple way here, link kinetic energy to the speed of something. The faster it's going, the more kinetic energy it has. Up here, it's going very slowly, but it's at a high point. So we can kind of think of the idea of height as potential energy, how high up it is. We're going to get into a little bit more detail on that, but that's kind of the basic idea. The higher up it is, the more potential energy it has. The faster it's going, the more kinetic energy it has. And you can see, just like we talked about before, the energy is transferred from one type of energy to another. As this goes down the hill, it's changing its energy from potential energy into kinetic energy. So what is kinetic energy? Kinetic energy is the energy of movement. If we look at these little bar graphs here, you can see, again, just like we talked about before, that the potential energy is highest when it's at the top of the hill. The kinetic energy is highest when it's at the bottom of the hill. A formula that you need to know in order to calculate kinetic energy is mass times velocity squared divided by 2. We'll use this formula a bit in class. Potential energy is the energy due to position, shape, or condition. So let's talk about those three things. There's three types of potential energy that you could have, and you can kind of see the three ideas right here. So our first one is called gravitational potential energy, and this is like what we talked about before. If you just simply pick an object up, it has more gravitational potential energy because it has the potential to fall once you let it go. And the higher you pick it up, the more potential it has to fall a longer distance. So as you pick something up higher and higher, you are giving it more and more gravitational potential energy. The second type is elastic potential energy, and I'm sure you can probably figure out what that is. When you stretch something out, like a rubber band or a spring or a piece of rubber or something like that, it kind of wants to go back to the way it was. Now, this all has to do with the way its atoms are arranged and things like that. We'll learn more about that later, but you understand this concept basically, that when you stretch something out, it kind of wants to go back to the way it was. So as you have it stretched out, it has lots of elastic potential energy. And the third and final one is chemical potential energy. And when you think of chemical potential energy, I want you to think of two things: batteries and food. Those things contain within them chemical potential energy, which then can be released in the form of electricity in the case of a battery, or it can be released in the form of energy that you have in your body in the case of food, like candy bars. All right, so let's talk about the different forms of energy we can have. We can really think of all of these different forms that we're about to talk about as being kind of different types of kinetic energy or potential energy, but let's kind of look at these different. So you'll be filling in this part of your notes, and as we go through this, just write down the name of the type of energy in the space provided, and then write the definitions in the space to the right. First, we have mechanical energy. So mechanical energy is kind of like what we've been talking about already, but it's the sum of kinetic and potential energy together. So you can imagine that at the top of the hill here, this car has pretty much all potential energy and no kinetic energy. At the bottom of the hill, the car has pretty much all kinetic energy and no potential energy. But what about somewhere in the middle of the hill? Well, in the middle of the hill, it has some amount of potential energy because it's got some height off of the ground, and some amount of kinetic energy because it's got some movement, some speed. So if we just added those two together, that would be its total mechanical energy. And one thing to think about is the idea that as the potential energy goes down, the kinetic energy goes up. So the total amount of mechanical energy in this situation here doesn't really change. You just have one energy going down while the other energy is going up. It's just trading off one type of energy for another. But the mechanical energy in this situation doesn't really change as long as we forget about friction, because remember, the whole time some of this energy is being lost due to friction, but that we'll talk about more of that later. All right, our second type is sound. Sound energy is caused by an object's vibration. Sound energy is both kinetic and potential energy. This, generally speaking, is energy that is caused by vibrating air molecules. That's usually how sound works. It's just jiggling air molecules. Our next type of energy is chemical energy. Chemical energy is the energy that is required to bond particles of matter. Chemical energy is a form of potential energy. This is something we'll talk about quite a bit in the second half of the year. We have electrical energy. Electrical energy is the energy of moving electrons. Electrons are part of an atom, and again, we'll talk about that more later, but that's actually why it's called electricity, because it's the movement of electrons. We have light. Light is something that we're going to study quite a bit, and light is kind of an odd thing. It's a little hard to say exactly what light is, but light is produced by the vibrations of electrically charged particles. We're just going to kind of leave it at that for right now. We'll get into the strangeness of light later. Next, we have heat, which is also called thermal energy. And as we talked about earlier, thermal energy is just the kinetic energy of particles that make up an object. In other words, it's how fast those particles are moving. And last but not least, we have nuclear energy. And nuclear energy is the energy that deals with changes in the nucleus, which is this part of the atom here, the center of the atom. And we'll talk about that more later. Don't worry about the bungee jumping egg thing. We'll do that in class. You can leave that blank. So to sum things up, we have the law of conservation of energy. Energy cannot be created or destroyed. We have the laws of thermodynamics, which starts off with the law of conservation of energy. We have energy being lost due to friction, like rubbing your hands together. We have heat equals the movement of atoms. Heat is just a measurement of how fast the atoms are moving. Kinetic energy and potential energy. We have kinetic energy is movement. Potential energy is sort of stored energy, and we have gravitational, elastic, and chemical. And then we have all the forms of energy, and all of those forms of energy that we talked about are something that we are going to go into a lot of detail throughout this part of the year. And so that's it. Don't forget to fill in all of your notes. Don't forget to tell me where the owl is, and don't forget to do your description. Thanks.